I just want to review a few topics from first semester. And so actually I'd like to start by answering the most common question that I get, which is, do I have to know everything from first semester? Are we going to be tested on first semester stuff? And the answer to that is complicated because really organic chemistry is like a 1-year course. It's really one course, but we divide it into two just to sort of package it for semesters. And if you were at a school that had quarters like UC Irvine, it would be a 1-year course to be divided into 3 pieces. They would just cut it at different places, okay? And the course does build. And so in a sense, yes, you need to know the stuff from first semester, but it's not my philosophy to, to the extent that we test, to test you on first semester material directly, unless it has been specifically reviewed in second semester. And that is the subtle point, is that we're going to go back and review some of our first semester material when it applies to second semester topics, because there's some topics, if you don't really remember the stuff from first semester, it won't make any sense, okay? And then you will be accountable for all of that, okay? So questions about that? Does that make sense? I will be trying to fix that the Canvas is open so you have access to the notes, that the mastering homework is back online so you can practice them. I'll see what I can do about that. I think there's a setting in my Canvas where I can open it to anyone at OCC, read only, so that you can like go and look at all the stuff, okay? Even if you weren't in the class last semester. I also want to point out that that YouTube link that was up there, that is actually the first lecture video for the chapter material. And I'll be posting that assignment. The assignment for that won't be due until the beginning of next week, but all of the YouTube videos from first semester are on there. I'm in the process of, I put them each in their own playlist. I'm going to just crunch them all into one playlist and try to get them in a decent order. But they're all there. And actually there's a link to a Google Drive that has actually copies of the notes also. So, okay. All righty, let's talk about first semester here. So this is not going to be everything that you need to know, but I just want to hit a couple of the important topics, some of which, depending on where you are or whatever, you may not have seen in detail, or you may have forgotten or whatever. So first of all, formal charges. So where did we get that slide? Oh, I'm going to be posting these notes, Cindy. I'm so sorry I didn't get them up there in advance. I was working on so many things and I just ran out of time. So it'll be posted. This is actually going to be module 00, which I'll be posting later today. It'll have a link to this recorded lecture. It'll have the notes, both empty and filled in, and it will have a link to the first homework assignment. Okay? So, alrighty, so formal charges. So the purpose of formal charges is just to sort of try to account for where there are an imbalance of protons and electrons, where there are essentially areas of positive or negative charge in a molecule. And the reason why they're important is that they provide us guidelines for predicting reactivity, because as you've probably already noticed, a lot of reactions are like something that has a negative charge is attracted to something with a positive charge. So if you know where the negative charge is and you know where the positive charge is, those are the parts that should interact. Okay. Alrighty. So to do formal charges, you have to have a complete Lewis structure. By complete Lewis structure, I mean you have to have a structure that has all the lone pairs on it. So if you've been given a structure that, for example, has an OH, there's no lone pairs on the oxygen, but you know they should be there, you got to add them. And so I typically start by being very explicit, but as we move on, I start leaving off lone pairs and assuming that you'll know that they're there, just because after a while it gets very tedious. Sometimes we're in a hurry. So then each atom would like to have a certain number of valence electrons. And the idea here is that when we look at an atom, it has this nucleus and there's these positive charges in the nucleus. And when the atom is neutral, for every positive charge in the nucleus, there's an electron circling it. But we know that the electrons are arranged in layers, right? And so when we look at a carbon atom, it has an inner layer of just 2 electrons, and then it has an outer layer of another 4. And we call the outer layer the valence electrons. So what we basically assume is that the inner electrons don't really change, and they'll be, you know, if there's 2 inner electrons, there's 2 of the positive charges in the nucleus are balanced. So it's just the outer electrons we've got to worry about, the valence electrons. So how many valence electrons will an atom want? Well, there's 2 ways to look at it. If we look at a periodic table, which, do I have one on my desktop? I should. Yeah, perfect. There we go. So here's a periodic table. What we see is that, and this is just really quick review, but what you know, hopefully you know, is that as we move across a row of the periodic table, we're adding a positive proton in the nucleus and we're adding an electron in the valence shell, right? So if we look, lithium, for example, has 2 electrons because it has 2 positive charges in its inner shell. And then we kind of reach the end, we come over here. Now we're starting a new layer, and that first layer has 1 positive charge, extra positive charge in the nucleus, and then 1 electron in that outer layer, right? And so carbon, for example, here, we can just count across the main group, which is the part that sticks up here, 1, 2, 3, 4 valence electrons. That's how many it starts with. That's many it'll have when it's neutral, right? The other thing you can do is you can, if you're comfortable with dot pictures, if you make a dot picture, which if you're not, don't worry about that, but this is just kind of review, you know, where you put dots on for the valence electrons, an atom is going to want the same number of valence electrons as it has dots in its dot picture. But usually you can just count across these main groups. That's how many valence electrons it should want. So then what we have to do is say, okay, it wants a certain number, but in this structure, how many does it actually own? And the idea with this is kind of based on Lewis, that when you have a bond between 2 atoms, the bond, the covalent bond, is caused by sharing electrons. So since there's 2 electrons in that bond, each atom, because they're sharing them, each atom gets 1. So it actually only owns 1, even though it's able to access the other electron it's sharing, right? So in contrast, if it has a pair of electrons on it that aren't being shared, it owns all of those electrons outright. So it owns 2 electrons for each lone pair, 1 electron for each bond, and that's each line. So a double bond counts as 2 bonds and so forth. And then if we have unpaired electrons, which we're going to see later this semester, it has 1 electron for those. So we total those up. And then the formal charge is really just a very simple arithmetic thing. You say, how many electrons does the atom want? And you subtract the number it currently owns. And that's going to give you a number. And that number is going to be either positive or negative. And we need to keep that sign because that number is the formal charge. So if it's a positive number, it's a positive formal charge. If it's a negative number, it's a negative formal charge. Now, when we write formal charges, what we typically do is we write the charge next to the atom in the Lewis structure, and we put a circle around it. Okay? That's to indicate that it's a formal charge. It's on that atom. And then just a really good way to check yourself is if you're working with an ion that has covalent bonds and you want to know whatever, okay, the overall charge on that ion will be the sum of the formal charges. And I'm going to show you an example of that really quickly. The other thing is that there's patterns for formal charge. And some of you are probably already have most of these memorized if you were here last semester. But here's the pattern. Since we mostly work with carbon, nitrogen, and oxygen, these are really by far, I would say, like 80 to 90% of the formal charges we're going to be dealing with. Okay. Carbon will be neutral when it has 4 bonds. A nitrogen will be neutral when it has 3 bonds and a lone pair. And oxygen will be a neutral when it has 2 bonds and 2 lone pairs. We work with carbons that have only 3 bonds and a positive charge a lot. When carbon has only 3 bonds and an empty space, it has a positive charge. When it has 3 bonds, but it has a lone pair, it has a negative charge. We're going to start seeing more of those this semester. In fact, in our first lecture, we're going to see those. And then nitrogen, when it has 4 bonds, nitrogen is a base, so sometimes it does acid-base and uses this pair of electrons to make a 4th bond. When it does that, the nitrogen gets a positive charge. And oxygen, you've encountered both of these. So for example, water HOH can use one of its lone pairs to make a bond to another proton, another hydrogen plus, right? And it becomes H3O, positive charge. And the reason for that is that oxygen now has bonds to 3 hydrogens, only 1 lone pair, positive charge, and so forth. So, okay. So feel free to refer to that table and feel free to memorize these patterns to save you some time calculating. But fundamentally, we should be able to work all of these out. So let me just give you some examples. I'm going to really quickly draw out a couple of examples here. Okay, so here's what I did here. All right. And I just, normally we're not going to do it this way, but again, this was kind of an early topic. So this is actually the Lewis structure of, I'll just put it down here. It's HSO4 minus ion, hydrogen sulfate ion. Okay. And so the overall structure has a minus charge. So to indicate that, I put it in brackets and put a minus on the outside. So I'm saying there's not necessarily a minus on any of these atoms, although there is, but that the sum of all of the formal charges is a -1. Okay? So let's look at some of these atoms. So hydrogen, I'm just going to show you this once. Hydrogen, when it's covalently bonded, never has a formal charge because hydrogen wants 1 electron. It's the very first one. It's got 1 positive charge in its nucleus. It only wants 1 electron. And in this case, if we look, it has 1 bond. So it owns 1 electron for that. So it owns 1 electron, 0 charge. So this is the great thing. We can ignore hydrogens when they are covalently bonded. Okay? Now let's look at this oxygen. So oxygen, it turns out, wants 6 electrons. Let's just really quickly go at the periodic table and see why that's the case. Starting on the left, counting, we go 1, 2, 3, 4, 5, 6. So it's in the 6th column. It wants 6 valence electrons. Again, these are numbers you'll probably memorize if you haven't already. If we look at this oxygen, it owns 1, 2, 3, 4, because it has the 2 lone pairs and it's not sharing those with anything. Then it owns 1 of the 2 electrons in this bond, so that's 5, and 1 of the 2 electrons in that bond, so that's 6. So that oxygen has 0 charge, and we don't have to do anything else. We don't write a 0 next to it, okay? But let's look at this oxygen right here, just so I have space. That oxygen also wants 6. But if we look, this oxygen owns 1, 2, 3, 4, 5, 6, right? Because it has 3 lone pairs, plus 1 for that bond. So it owns 7. 6 minus 7, -1. So what we do is we put a minus in a circle next to that oxygen. Now I'm not going to redo that, but can you see that these other oxygens should also have minuses? So there's lots of charges in this molecule, right? Finally, let's look at the sulfur. So if we look at our periodic table, sulfur is right underneath oxygen. So when we do our counting thing, 1, 2, 3, 4, 5, 6, it also wants 6, just like oxygen. Okay? That's a good question. I'll talk to you. Somebody just asked about expanded octet. I'll mention that in just a moment. Okay? Yes, it can. It doesn't have to, but it can. All right, so let's look at the sulfur, and then I'll get to the expanded octet issue. So the sulfur wants 6, but it has just 4 bonds to it. So that means it only owns 4. So that 6 minus 4 is positive 2. What that means is that that central sulfur has a +2 formal charge. It's highly charged. Okay? Which is probably not surprising because those oxygens are really electronegative. They're pulling electrons away, right? And so now if we look here, do you see? The 3 minuses and the 2 pluses add up to being just 1 minus overall. That's the overall charge. Okay, now let's really quickly talk about expanded octets. Okay, so many chemists prefer, and in fact I do when I'm lazy, prefer to draw things like hydrogen sulfate and sulfuric acid where we have a central third row atom. Okay? They prefer to move the electrons around a little bit to minimize the formal charges. And what you basically do is if you have a third row atom that has a positive charge, what you can do is you can find if there's an adjacent atom that has a negative charge, you can take a pair of electrons and move it to make a second bond in between those. So I'm going to do this twice. Okay? And what this does, if we look at this sulfur now, it wants 6, but now because it has 6 bonds, it owns 6 electrons, has 0 formal charge, okay? And we call this, because there's 6 bonds here, we call that an expanded octet. And again, this is probably review for most of you. That's cool. I just wanted to point it out. Remember, we're only allowed to do this on third row or higher only. Second rows never have an expanded octet, okay? So that's just a really quick review of formal charges. I think I have a little problem in there. Okay, so let's talk about that really quick. Are both forms equal in stability? Okay, so without getting too philosophical, I have 2 things to say. So first of all, actually, well, okay, let me put it this way. The short answer is no, because the second form has 2 things to its advantage. The first is that it has more bonds. And when you form a covalent bond, you lower the potential energy of a molecule. So structures with more bonds are more stable. Furthermore, it has fewer formal charges, which is also a desirable thing. The problem is, how do we justify this? And actually, there is a justification for this in the bonding theory that says that the sulfur has empty d orbitals that the oxygens can essentially make a pi-like bond with. It's called p pi to d pi back bonding. And so that should potentially, if they do calculations, that lowers the thing. So that's why they justify this. There's sometimes when you don't really care, and there's sometimes when actually using the octet rule follower gains us something. We get more information, okay? So you can draw either one in most cases. Again, I quite frankly, I usually draw this one when I'm being lazy. Excuse me. Where's my thing here? And I'm an organic chemist, so I'm feeling lazy a lot. So, okay. All right.